Welcome to the SSI Orbit podcast, a forum for conversations that explore the ever-growing ecosystems of self-sovereign identity. And I'm your host, Mathieu. We've done this before. It's coming up on a year, I think, since we've last done this, which is kind of crazy. But we often talk about the internet being broken, and the reason why we do a lot of what we do in the digital trust space. Is the internet broken because of security, privacy, authenticity, and confidentiality? These four pieces, SPAC, is this kind of a good framing for why the internet is broken and why we're doing what we're doing in the trust over IP and just general digital trust space?
The short answer is yes, but I want to qualify that. I personally have sort of reaction if you try and tell people at a cocktail party, "Ah, yeah, the internet's broken." Most folks will look at you and sort of go, "Yeah, well, I'm using it every single day for my whole digital life. So what exactly is broken?" So I like to narrow it down a little bit more. I do like the point I'm hearing it more and more. The internet doesn't have a trust layer. And so, and all four of those things you mentioned, Mathieu, are the elements of a trust layer, and it is absolutely missing a trust layer, and it has even been acknowledged by the founders, original architects of the internet, that it was just beyond their scope and their ability at the time that they were crafting it to deal with issues of authenticity and confidentiality, privacy. It's just they didn't have all the tools it would take, and furthermore, they didn't recognize the problem it would become. And I don't blame them. For anyone who's interested in diving into understanding that better, there's a series, a whole series of Washington Post did, I think, about 2012 on why the internet is missing a security layer. I'm trying to remember the name of the series, but it's really good, and it goes into it in great depth, and that's why we need to fix it.
Yeah, I remember seeing them linked in the Trust over IP technology architecture reference document, and we'll link them in the show notes as well. I remember they being quite a good read, and the kind of builders of the internet just purposely choosing not to do this, which the decisions they made obviously led to mass adoption and massive digital transformation that we're still seeing today. So it's kind of, can't say that it's not a success, but I guess as you mentioned, the proper framing maybe is there isn't a trust layer, which is evident if you walk into a cybersecurity conference and seeing all the different vendors and all the different patches and solutions that are trying to be pushed to solve different problems or vulnerabilities that exist on top of the internet today. To fix this is kind of this looking, and I don't know if this is the right lens, and if there are kind of more things that are broken or result in lack of trust on top of the internet. But this SPAC acronym, which we're going to start using, security, privacy, authenticity, and confidentiality, is that kind of the core principles that are behind the creation of this trust spanning protocol? Like, is that good framing for that? And perhaps we have talked about the trust spanning protocol in previous podcasts, but it may be useful to just take a step back again and kind of give a basics of the genesis of this, how it came about. And again, is this SPAC concept a good framing for the ideas behind the trust spanning protocol?
Absolutely. And it is a good framing for it. And I will back up a little bit of context, especially for folks listening to this, that haven't listened to the earlier podcast. Trust over IP is so named, and it was named by John Jordan, who is the executive director of digital trust services for the government of BC in your home country of Canada. And he came up with that name because as what we call decentralized identity, or SSI, self-sovereign identity architecture matured, it became clear to us. It was like, oh, this could be the basis, this general model for a trust layer for the internet. But if we want to turn it into that, we need to follow the same design principles as much of the internet itself. And some of those design principles actually weren't even clear necessarily the original internet architects. There were some that were, and then after it succeeded beyond everyone's wildest dreams, they also looked back at it and said, well, why did it work the way it did? And the internet stack, often called the TCP/IP stack for the TCP protocol, which is layered over the IP protocol, it follows a particular model known as the hourglass model. And it means that there are protocols at the bottom layers that support the higher layers. But most importantly, those lower level protocols all go up the hourglass, and at the neck, the thin neck, is a single protocol called the spanning protocol. And it's got a very particular design philosophy for a spanning protocol. And then above the spanning protocol, the hourglass widens up again to support whatever protocols above it that need to provide certain kinds of functionality to support certain kinds of applications. But what makes them all interoperable, what makes them all work together, is the fact that they all work down and through the spanning layer, which is one protocol or one very tightly designed small suite of protocols that then are supported by all the protocols down below. And for instance, with the internet and with TCP/IP, what they were trying to do, all the supporting protocols were all the different networking protocols you had to move data around on local area networks. But what they didn't have was a way to connect all those local area networks into a global internet. So they said, well, to do that, we need to come up with an addressing system, an addressing layer, and a standard way of moving messages across those networks, moving data packets across between those local area networks. And so that's became the IP, the internet protocol, and that is the spanning layer. And the goal of the spanning layer is to keep it as simple as you can, as simple as possible, but no simpler, to follow the Einsteinian dictum. Because the simpler it is, the more universal it is, the more interoperability you get. So you need it to do just enough to allow the supporting protocols below to connect to the supported protocols above it. And that design is, as we've said, worked in spades for the internet and all the protocols. So when we use that term TCP/IP, it's because TCP is actually a protocol, transmission control protocol, built right on top of IP. And it actually provides session functions and other things to control the movement of packets over IP in a connection-oriented way. And they didn't initially, until they needed it, say, oh, we need another one, another protocol at that layer right above called UDP, because we need a connectionless way for packets to flow for scaling and certain other purposes. And they're not the only two, but they're the two best known protocols just above IP. So you end out again with a small set, and then above those we have all the protocols, SMTP that is what we use for email, and HTTP and HTTPS for the web, and all the other protocols, VoIP, I point out, voice over IP for handling voice, that make the internet so rich. But in that stack, in the TCP/IP stack, as we started this podcast, they didn't include solutions for security, authenticity, privacy, confidentiality. It's not like it was completely ignored, but they didn't build in the architecture for doing that. So the aha that came to us as SSI was maturing was to say, oh, what we really need is another hourglass, a second stack that can work on top of the TCP/IP stack, so that, and that stack, the supporting protocols are the internet protocols, the TCP/IP stack, or other protocols like NFC or Bluetooth Low Energy or 5G, whatever it is that's going to move the data around. We're going to do another hourglass, but this hourglass is going to be designed to solve the trust problem. with those four magical properties. And that stack also needs a spanning protocol. And that is what we call the trust over IP spanning protocol. And after we did our our design principles in 2021 and our architecture specification in 2022, we started this year in January with the launch of the task force we needed to say, well, no one else is working on a trust spanning protocol that meets this design, so we're going to do it at Trust over IP and the Trust Spanning Protocol Task Force.
Talking about IP and the IP address as an identifier, and that is going to lead us in nicely to one of the first pillars of the design of the trust spanning protocol. But before we get there, as kind of this work was happening, as the Trust over IP's Trust Spanning Protocol Task Force went through kind of the design principles phases, and then started getting more formal with discussions and going through different proposals of what this could look like. What were kind of some key differences in some of the approaches, or maybe the better question is, were there concessions that had to be made between kind of the balance of security, privacy, authenticity, or confidentiality, or is this something that could kind of all be achieved at maximum levels if you want to? Were there any concessions that had to be made, or just like the builders on the internet had to make concessions of what to do, what not to do? Were there any of these critical decisions that happened during kind of through the proposal phases, but more after, I guess, during the consolidation phases as all the different proposals were looked at?
Yeah, it's a very good question. And those two stages, I'm going to point out, we just for the convenience of the different working groups and task forces at Trust over IP, we created it's on our wiki page. You can put a link to it in the show notes, a table of the 10 stages that working groups and task forces go through if they're going to produce a deliverable, especially a specification. And the two that you referred to, what we call the proposal stage, and then followed by the consolidation stage, are sort of at the very middle of the process, the very center of it. And at the proposal stage, so the stages before that, you're basically all getting on the same page. You're agreeing as to the problem and the scope of the problem, and then, once everyone's, and there's several things we recommend doing to really get that clear, then you need proposals, and proposals are specifically members of the task force working group to say, hey, here's how we think, or I think we should solve the problem, either the whole problem or some aspect of the problem. Proposals come forward, and we had, as the blog post covers, we had four, sort of complete proposals or design proposals, which, interesting enough, they weren't. I would say they weren't directly competing. They all came at the problem from sort of a somewhat different perspective. They definitely intersected in a major way, but they were all different perspectives on it. And so once we got through that and we entered what we call the consolidation stage, which is frankly the hardest part of the work, it's one problem if you don't have proposed solutions, you can't figure out, or you just got to spend a lot of time trying to figure out solutions. It's a different problem if you have a bunch of different competing proposals. And either way, the idea is you got to consolidate into something that can then become a working draft, and you start working the issues, narrowing it down until you got a final draft. So in our case, to answer your question, Mathieu, it wasn't really a matter of so much making concessions as it was consolidating these four different viewpoints on the problem space. And they did have, there were some sort of design considerations that didn't necessarily agree, and there was more emphasis in some cases on some of the proposals on the security aspect or the authenticity aspect or the privacy and confidentiality. I'd say the biggest thing that happened in both in the proposal stage and consolidation was everyone in the task force coming to a much deeper understanding of the problem space and the considerations for all four of those things. There are some trade-offs involved, but the class-wide perception that security and privacy, for instance, are, it's a zero-sum game, and if you get greater security, you get less privacy. That's a complete fallacy. And again, there are trade-offs. I think the most important thing we discovered, though, was it comes down to layering and how you layer it, how you design it. So which problems are tackled at which layer. That's where we finally got to, to rough consensus, as we put it in the blog post. It's not 100%, but it's very close, far enough for us to now then enter the working draft stage, which is why we published this blog post of what we call the 7 design pillars. And the last thing I'll say in terms of that is, when we got to these 7 pillars, which came out of some sort of intensive work we did between some extended meetings. We said our 1-hour weekly meetings are not enough, so we scheduled some 2-hour workshops, and we used every inch of those 2 hours. And then we finally had some extensive discussions and GitHub discussions, a great tool for really in-depth technical discussions. And finally, a handful of in-person small group meetings. That's where we finally broke the back. And when we came up with these 7 design pillars, folks were really excited, because we said, hey, if we approach the design this way, we really have consolidated the vast majority of views, and we think we've got something that can meet all 4 of the SPAC requirements.
That's fantastic. And so you kind of lead into the 7 pillars of the design, and there's a bunch of references we're talking about here. So please check out the show notes if you're interested. You don't know where to find these things, but the Trust over IP published a mid-year progress report of the Trust over IP trust spanning protocol, and describing the 7 pillars of the design, which Drummond just referenced to. So if we kind of jump into that, because I think that will be very helpful for folks just to understand the different pieces of this, and then just to understand where it's at and where it's moving based on this. The first pillar has to do with identifiers. So we talked about the internet having identifiers. We have a different type of identifier inside of the self-sovereign identity digital trust space. Maybe you could talk about that to begin with as the first key pillar of the design of the trust spanning protocol.
I would be more than happy to, and a lot of folks that know me are going to expect the next words out of my mouth are, well, of course, it's decentralized identifiers, DIDs. And they will be surprised that I'm not going to say that. I'm going to use a different, slightly broader term, verifiable identifiers. And there's a very good reason for that. And if folks have read our technology architecture spec, which links to all this, if you go to this blog post, all these other things we're talking about are linked here. So that'll make it easy. The reason we use that term is because while DIDs are a perfect example, they were created, they're 100% verifiable identifiers. We realized that there's a slightly broader category. What we define a verifiable identifier is cryptographic, that you can prove cryptographic control over the identifier. And it turns out that there are a couple other requirements as well, but you can do that with other identifiers besides DIDs. And so we wanted to, for instance, if you have the right wrapping or set of specifications around using an HTTPS address, the form of URL we use for encrypted communications on the internet today, it can be serve as a verifiable identifier. X509 identifiers are backed by public key certificates. Again, with the right additional tooling, can work as verifiable identifiers. So we wanted to be inclusive of existing public key infrastructure and cryptographic verifiability. And we didn't invent that at Trust over IP or even recently. It's been around for a long time. What we're doing is harnessing it and saying that what we really need for a trust spanning protocol is cryptographically verifiable identifiers that can be resolved to the two things you need: the current public key, or quote verification method for that identifier, and the endpoint or endpoints on the network where you can talk to the entity represented or identified by that identifier. It might be a person, but it might be an organization. It might be a connected thing. It might be a database. It might be a single document. It might be an AI. Anything you can identify, if you have a verifiable identifier for it, you can solve the first and most important problem, which is you can actually know that you're talking to the authentic entity, right? So that's why the starting point for the internet was an identifier that could route data any place on the internet. And that solved a huge swath of problems. The starting point for trust over IP for our spanning protocol is a verifiable identifier that you can verify the communications that you're making on it. And again, it solves a different kind but very similar problem, and that's why it's the starting point.
Do you foresee endpoints having to support the same types of identifiers? Meaning, does interoperability over the trust spanning protocol depend on similar identifiers being used? Like, will there be different interoperability profiles down the road for this? And then maybe a second part of that question is, how does one endpoint kind of evaluate or judge the other endpoint's capability to support an identifier or another one?
It's a very, very good question. When we first started work on DIDs, I think it was 8 years ago at this point, I anticipated that there would, one of the breakthroughs was to say, hey, there's not going to be just one way to do a DID. There's going to be an overall specification, but then different, what we call DID methods, because binding an identifier to a key pair on an endpoint there are a bunch of different ways you can do it. And they have different security properties and potentially different privacy properties and scalability and decentralization properties. So we didn't want to say there's one way to do it. We wanted to say there's one standard form of the identifier, and there's one standard result when you resolve it and get it back. So that's the interoperability we were after. What I didn't anticipate is that at this point, we have over 160 DID methods. And so there's really a very wide variety. And they're not just, I want to emphasize, many of them are based on blockchains. Not all are based on blockchains. We turned around and realized, there are many other ways to bind an identifier to a cryptographic key that don't. One of the early ones, the peer DID method. Two peers are basically generating key pairs, generating DIDs from that, and then exchanging the documents directly. And they can each, as they rotate keys and everything, they just are basically communicating updates to the DID documents to each other. And then there's a very strong form called autonomous or autonomic identifiers, AIDs, where the identifier is bound to the key pair cryptographically, so you don't need any, blockchain or database or anything else. If you have the record of the key states associated with that identifier, you can prove from the first one all the way through all the key changes. You can verify the whole chain, and that's the KERI architecture. KERI uses autonomic identifiers. So we wanted to support all of them. And to answer your question now, the two parties or n number of parties that want to communicate using the trust spanning protocol are going to have to be able to understand each other's identifiers and the cryptographic algorithms that they're using for verification. So they will have to agree, but they don't necessarily have to, we don't have to edict that there's just one way to do it. I personally believe what's going to apply is the power law. It's exactly what's happened, for instance, with URLs on the internet, or technically URIs. Your browser can understand many different URIs, those strings that go at the start of HTTP or SMTP or FTP or everything else. there are, at last count, I think there are over 360 of those registered with IANA, but we only see a handful in broad usage, and that's what I think is going to happen. It's going to be a Darwinian survival of the fittest in terms of the types of VIDs, VIDs that end out being used as folks, as different implementations start to multiply out there. And we do, because of that, though, we have a very important feature that we agreed on that needs to be in the Trust Mining Protocol spec. We call it an appraisability framework. And what it means is, for whatever VID you're connecting to or wanting to talk to, there needs to be a standard way for you to request a verifiable description of what security and privacy parameters and infrastructure parameters are behind that identifier. It doesn't mean just the type of DID method or AID method it's using, but also what kind of blockchain or database is it using. There's some other factors there, and what we want to standardize is how you describe it, so that the party that the verifier, relying party that's going to be talking to that VID can say, yes, that meets my requirements, or no, it doesn't.
Could that appraisability framework be a trust task? Like, it kind of, there's discovery as part of it. Like, for what reason does it have to be on that second layer? And maybe like, could it be a higher layered trust task that is used?
So that is a very good question, as usual. First, let's just define this term trust task, because we're going to use it quite a bit as we go through this. A trust task refers to a protocol at the next layer up, at layer 3 of the trust IP stack. Something that is a standard function or workflow that two or more parties need to go through to achieve a trust objective of some kind. And so you're right, Matthew. You could say, well, I have your VID. I want to request the appraisability framework instance for your VID, that I can ask for that at a higher level using a trust task that we define over the higher level protocol. The reason we put it down at this layer is because decisions about trusting the other identifier are fundamental. They, in other words, if for some reason you don't trust the identifier, then no trust task at a higher layer, you're not going to trust anything at a higher layer. You have to, the security or privacy or confidentiality of any higher layer cannot be better than what you establish at layer 2. Because if layer 2 is weak, then you can't build on a weak foundation and make it stronger, by piling things on top. You have to have the foundation. You have to get the foundation to the strength you need. And so that's why we have appraisability. Now, whether or not the retrieval or any negotiation on the appraisability becomes something that we layer in as a trust task, or some portion of it, I don't know. We're going to, we're diving into the working draft stage now, and I think there's a number of things that may be layered in that we say it's not an absolute requirement at layer 2 in the spanning protocol itself. But we'll get more into the sort of the choices, those design choices, as we go through this.
Fantastic. And so moving to the second key pillar out of the 7 of them. So we just covered verifiable identifiers. The second one is called end-to-end authenticity and confidentiality, and using the acronym ESSR. And this seems to be an element that which is nice in kind of this architecture, is that there is some composability and reusability. This is kind of a way of doing encryption that has existed before, that's been able to be leveraged to achieve the design principles of authenticity and confidentiality. Let's maybe go through it and touch upon the ESSR principle?
I'll keep it as simple as I can. I myself, I'm not a cryptographer. I'm not a cryptographic engineer. I'm not even a developer. I call myself a connoisseur of these brilliant folks. And I was not aware. I was aware of the problem. Is actually fairly easy to describe. When you're using public-private key cryptography, asymmetric cryptography, there are two different operations you need to do. And the one we're all familiar with is encrypting messages. You're going to encrypt something with a private key and excuse me, encrypt something with a public key, and then the party that has the private key can decrypt it. So you're able to control who can read certain information that you're sharing. But as you get into it, there's a separate property of digitally signing information. And when you're signing it, you're using a private key to generate a signature that only you can generate. And then anyone who has your public key can then verify, oh, that really was signed by whoever had the private key. So I like to call them symmetric operations. They work in opposite ways with key pairs, and they can use different key pairs, right? You can sign with one cryptographic algorithm and encrypt with another one. In any case, that's the sort of basics of it. So the fact that there are those ways meant that, and again, I got an education on this from the architects and cryptographers that are part of the task force, that since you can do both these things, what's the right combination that actually gives you both the strongest authenticity, the best security, but also the best confidentiality? Because there are all these kinds of attacks you can do on cryptographic algorithms. And what ESSR stands for is encrypt the sender's key in the encrypted message and then sign the message. But when you sign it, you also sign the receiver's key. And it turns out if you do that you include the sender's key in the portion you're encrypting, and you then sign the receiver's key as part of the whole package, you're defeating a number of attacks that you can make if you don't do those two things. And that's the simplest way. I mean, even in this is the shortest explanation of the 7 we have in here, because we just refer off to some excellent papers and several blog posts that summarize this in a lot more depth, which I want to say is pretty accessible if you're interested at all in cryptography. You don't have to be a cryptographic engineer to read these references. Our key point is, as we go through the rest of these, you're going to see we're going to start layering protocols. All of them use the ESSR pattern. We're just baking it in. That's why it's design pillar number 2.
So the third pillar, so we've discussed verifiable identifiers, ESSR, which is going to be used across the board. So I'm sure we'll hear more about it as we go through these pillars of the design. But the third pillar is about connections and direct connections using different types of channels. So this would be the next one to kind of explain and go through for the folks.
You bet. And so as folks understand, with ESSR, we've really said this is how we're going to tackle authenticity and confidentiality. So as we get to the privacy point, I like to make sure that we make the distinction when you're talking about privacy of shared data. When you've shared data with another party and they have received it and decrypted it and it's in their hands, what they do with that data, what I call usage privacy, is not something we can protect with technology, right? The data is in the clear, in their hands. That is a matter of a different kind of trust, right? It's contractual trust or human trust. And there are various different things we can do, but not with technology, with law and social expectations, reputation systems, all that kind of stuff. So what we're trying to tackle here with this design, the pillar number 3, is what we call correlation privacy, which is often called, observable metadata. How much can you see based on the traffic on the network? How much can you learn about the parties and basically surveil what they're doing, even though you can't read the messages or necessarily know exactly who are at those endpoints, right? And so to tackle correlation privacy, we're going to do the two steps. We're going to do the third pillar is about how we can handle it on what we call a direct channel connecting endpoint A to endpoint B. And when we use that term endpoint, it's a very specific term in our architecture. And it really is the same thing as the internet endpoint. It's any device or entity on the internet that can speak the protocol to another device or entity on the internet. So yes, we're talking phone to phone, any kind of computing device, but it could also be, an endpoint could be a server, something in the cloud, an IoT device, any two things that can connect with each other just the way they could connect down at the IP layer over the internet. So that's what we call a trustworthy endpoint. And the essence of the third pillar is we're going to provide the first step towards correlation privacy by nesting two channels. And we just call it the outer channel and the inner channel. Now, both of them, the channels identified by the two parties exchanging VIDs, verifiable identifiers. But in the outer channel, those verifiable identifiers are visible, right? It's like an IP address on the internet. If you can monitor the traffic, you can see it's going from this IP address to that IP address. And we're saying, yep, there's no way to prevent that. So we're going to say that outer channel, those two verifiable identifiers you're going to be able to see them. You're going to be able to see in our examples here in the blog post, we talk about A and B. So A and B, you're going to be able to see that there is a connection, traffic flowing over the two. You can't read it. You don't necessarily know who A and B are, but if you can find a way to surveil it enough, you may be able to figure that out. But what we say is we can get to partial correlation privacy if inside that publicly visible channel, there's a separate channel we call the inner channel. And that also has a pair of VIDs. And but those two VIDs are private, meaning because they are only A knows the VID that he's sharing with B, or he or she, and only B, if we're talking Alice and Bob, only Bob knows the VID that he's sharing with Alice. So, and what they're going to do is they're going to use those two private VIDs to communicate over that channel. And so that there's traffic there, you can see it publicly, but you actually don't even know the identifiers they're using to communicate. Which means if they switch to another outer channel, they can keep using the private identifiers they've been using on the inner channel, still know that they're, going to have the same connection, but now it's flowing through a different path over the internet or whatever communications network they're using. So you're getting one step towards correlation privacy, between those parties, even if you can observe that they are communicating directly. So that's our third pillar. Like I said, the first of two steps towards correlation privacy.
And then it seems like the endpoints are obviously verifiable identifiers, which was the first principle we talked about. And is ESSR, the second one we talked about, kind of embedded within these channels that you're describing?
Yes, I should have pointed that out. Both of these channels, the outer channel, all the messages use ESSR, and the channel that is nested or tunneled inside of that, all the messages use ESSR. So it's you have you're baking in the authenticity and confidentiality at the strongest strength. Now you can use different strengths of cryptographic algorithms to get even higher degrees of that, but the basic core design is ESSR on the outer channel and on the inner channel. So you're just, one analogy I like to use is if you think of what we've built the internet with today, it's really fine. I've been a carpenter in my past life. I still am when I'm doing projects, building with really, fine grains and grades of wood. But with the ESSR, what we're moving to steel. right? And we're going to have a outer pipe and an inner pipe, and they're just a lot stronger. And you can, support it, build a lot stronger infrastructure, and support bigger and more ambitious projects that won't collapse under the weight of their security and privacy requirements.
And then why can I only achieve partial correlation privacy using this method? And then how does it, if I have a scenario where I need to have full correlation privacy, how do I do that? Maybe that kind of leads into the fourth pillar of the design.
It absolutely does. So as I have said several times here, with a direct connection, when A and B are communicating directly, you can't hide that fact if it's happening over a public observable network like the internet. So if you want to, not be able to reveal that A and B are communicating, if you want to not correlate their communications, you need to, at least our conclusion was there was no clear way to do that without introducing what in trust and PR architecture we call intermediaries. And intermediaries are is sort of up at our layer. They're similar to what routers handle on at the internet layer with TCP/IP. That they're how the packets get routed around the network. And if you're just exchanging packets directly between two devices, you don't need any routers. But as soon as you want to route them around a global internet, you have to have routers, and it's the routing protocols that get extremely sophisticated. And you've got huge companies like Cisco and its competitors that compete in that business. So what we said is both for scalability, but also for full correlation privacy or nearly full correlation privacy. As soon as you start using intermediaries, you can cloak who is talking to who, and you can do it by nesting one more layer. So instead of two layers or one channel tunnel inside another, we go to three. And the outer channel is still the same, and it's still direct between any two parties. And to be clear here, I'm going to. We have a diagram in the blog post, but I'm going to orally just say you've got, instead of endpoint A talking directly to endpoint B, endpoint A will talk to intermediary A. In this example, we're going to use two intermediaries. Endpoint A has its own intermediary. Endpoint B, Bob, has its intermediary. So they both have the same outer channel. You can still observe that there's traffic going back and forth between Alice and her intermediary and Bob and his intermediary. And you can also observe that those two intermediaries have an outer channel between the two of them. So you can go, oh, okay, there's, there are relationships there, but you don't know what they are. Now, you also still have the inner channel between Alice and Bob using those same two identifiers that they could use over a direct channel. They're going to be completely private to the two of them. What makes it all work via intermediaries is the routing channel in the middle. So the inner channel is nested in the routing channel is nested in the outer channel. And what the routing channel does is carry the information that intermediary, when Alice talks to her intermediary over that routing channel, she sends just enough information for her intermediary to be able to get the message to Bob's intermediary. And the routing protocol then when it gets to Bob's intermediary, there's just enough information for Bob's intermediary to route it to Bob. And in this design, if you can't observe over the public internet or any publicly observable network that a message is going from Alice to Bob from one endpoint to another. You can see the traffic going to her intermediary and between the intermediaries and between from Bob's intermediary to him, but you don't know what messages are traveling over that. You can't actually tell that Alice and Bob are talking. And if you break into or compromise intermediary A, you will be able to see that there are messages from Alice that are getting passed on, but you won't be able to. You'd have to break into intermediary A and compromise it there, and then also compromise intermediary B in order to put together all the information that a message is routing all the way from Alice to Bob. And the more intermediaries you add, the more you'd have to compromise to learn a complete routing path. It's basically a very simple, and it's accomplishing through channel nesting what otherwise would require onion routing.
So I think that's a helpful comparison to how packets are routed across the internet. You mentioned a company like Cisco in that market. What would like a practical implementation of this look like? Because now all of a sudden we've introduced some infrastructure or utility companies to the mix, right? I have my two endpoints that want to talk to each other, but if they want that high integrity to the max correlation privacy, then they'll want to use these intermediaries. How do you foresee, and I know we're still at an early stage in this, but how do you see this kind of evolving in the future? Does it become kind of another piece of the offerings of companies like Cisco just to facilitate digital trust, or these complete correlation privacy interactions between two endpoints, whatever they are? How does a practical implementation of this look like, do you think, in the future?
I am going to be fascinated to see. I think every option you just mentioned and more, that it's a pretty obvious step up. You know, if you go back to our original analogy of this trust layer and a whole second stack on top of the TCP/IP stack, well, the purveyors of the first stack, the routing layer for that, they're obvious choices. They could provide these trustworthy intermediaries. However, so could telcos that are routing our telco traffic today, are POTS, plain old telephone service traffic, and are deeply involved in internet routing as well. But one of the most obvious analogies, actually, Mathieu, is how are our secure chat messages getting to each other today, right? What's your favorite secure chat application, Mathieu?
I would have to go with Signal.
All right. So when you and I communicate over Signal, are our two phones talking directly to each other to route those Signal messages?
I believe there's some intermediary providing this service.
And that intermediary would be Signal. Now, I think one of the reasons you and I both use Signal, among the others, is because Signal is a nonprofit whose job is and public mission is to protect the privacy of that communications metadata. By the way, there's I'm trying to remember her name, Meredith, the CEO, has several recent fantastic blog posts about privacy and encryption and some of the legislative challenges to those things. But my point is, there is to scale secure messaging. There are always intermediaries of some kind, and we're relying on those. You just literally, you can name whether it's Signal, it's Telegram, obviously it's Facebook with both WhatsApp and Facebook Messenger, or it's Apple routing our iMessages. They're providing end-to-end encryption, but they are providing the only intermediary services. And you contrast that with the most widely used messaging infrastructure, electronic messaging infrastructure in the world today, which is SMTP email. And there we don't have, no one has a monopoly on SMTP servers that serve as those intermediaries for all of us exchanging email. That's an open standard. Anyone can use it and compete with it. And it's market driven, and maybe it can even be regulated to ensure that everyone has access. So this infrastructure we're talking about, Mathieu, to be very clear about it, we're designing what could become the what we were intending for this protocol to become a universally available, secure and private messaging layer that can be used for for synchronous chat, just like those other services, but also asynchronous message delivery, very much like email, and even other kinds of messaging that require more specialized protocols. Of course, that's what we would refer to as trust tasks, but all using a common standard layer for delivering the messages with exactly what we've been talking about, these first four pillars: standard way, authenticity, confidentiality, and privacy, which gives you the overall security that you need to be really confident in the infrastructure. Does that all make sense?
It all makes sense. So would the biggest innovation, at least for the intermediary here versus an intermediary like Signal or any of the others, just be that it's standardized, it's an open market, so you're not dependent or reliant on one, and whatever the protocols are, security protocols, privacy protocols you want to push forward here, like you'll make sure that you have the strongest available, and because you have optionality, it gives you that flexibility as any endpoint to decide kind of through what intermediary you want to go. Yes,
exactly. And I hope what emerges out of this, and it's going to take a while, but we have basically the first intermediaries coming on saying, hey, we need this protocol to do the things to solve an immediate set of problems, provide an immediate set of services. And then just like with SMTP email, right, the first one comes on, the second one comes on, and the network effect starts to kick in because it is an open standard and because it does provide the benefits. I personally believe as we get further into it and we start talking about the trust tasks and the actual problems we can solve, that's what will drive demand for the infrastructure. And what will happen is market forces, hopefully, like we said, companies like Cisco or existing secure messaging providers or telcos or all of them start to jump in and go, all right, now we've got an open standard protocol that has all these features. Let's start building infrastructure on it.
Perfect. So as we move now to the fifth pillar out of the 7 pillars, so just to summarize where we're at, we discussed verifiable identifiers. We described end-to-end authenticity and confidentiality. We described direct connections through inner and outer channels. We've described routing through intermediaries, routing channels. And the fifth one now that we get into is now, what if my two endpoints kind of want to change the type of conversation they're having between each other? What if the context in the interaction changes? Maybe I want to increase the level of secrecy or use different crypto algorithms. Maybe I want to do higher value transactions versus lower value transactions, in some cases via others. Maybe I want to stream data versus just sending individual messages. So the fifth pillar is about relationship, context, channels.
And you just did a wonderful job of describing it. I mean, yeah, seriously, it's this actually is one of my very favorite things. This is when we really saw what the double or triple layering would do. What we got most excited about is that once you've established, as you said, either direct or a routed connection, you have this inner channel that really doubles as a communications channel, but a channel that you can both use. And so we say this now can be a control channel. And one of the most important things you can do with that control channel is spawn additional channels. And it's interesting that the terms, I'm not sure we're done in terms of naming exactly. We ended up finally saying every new channel establishes a new relationship context, a new context for two or more parties to be, carrying out interactions, conversations, transactions, trust tasks, right? Whatever they may be. But they're able now, and it's funny, I do like the term channel. I know it's very overloaded, overused, but just think about the channels we're now used to using in team chat applications, right? whether it's Slack or Teams or whatever you might use, a Discord. Channels are extremely useful for establishing context, for helping us narrow our attention and not have to repeat a bunch of information. And then, of course, the threading you can do within a channel. And the idea of now being able to say, hey, we can have channels for anything, right? They can be about, semantic context, sort of like, Slack channels, just differentiate what we're talking about. But they can also be about, as you just said, hey, we need a higher, you're talking to your bank and you're wanting to move, $50 million. Well, they might want to say, okay, we're going to step up to a very high security channel, and we're going to require in the setup of that that you're going to do, higher level authentication, maybe a liveness check, possibly even require the use of a multi-sig for the messages going on that channel, right? All that can be part of the setup and configuration for a particular trust task that uses that channel or set of trust tasks, and all of that can happen. Again, even the setup is all happening with the authenticity and confidentiality we've already established in that very first intercontrol channel. So we think this is just going to give us a very strong foundation now for applying all these different needs for communication and context to every way that we might want to interact. One person on the task force put it to me this way: it's like, wait a minute, this is how digital communications can start to have some of the nuance, some of the inflection and dimension of human face-to-face communications, right? And we're starting to build it into our digital infrastructure. So I'm very excited about this because of what it will set up for the trust task we'll get to in a minute.
Perfect. And yeah, I wish with the amount of times I sent $50 million all over the place that I had higher levels of authentication and ID verification to go along with that. So looking forward to this. It kind of fits in also to you could have different personas based on different contexts as well between two parties too. So I really like how it just, like you said, molds into a more human type of behavior or interaction. The sixth principle is more of a way for two endpoints to, I guess, organize and understand events using a common language. Is that fair in describing what the sixth pillar is, which is about text and binary encoding?
Yeah, the sixth, I have to say, based on my again, I'm not a developer, but I have been spent much more of my life than I ever expected on these very basic, call it sort of foundational building block or building blocks, and they come down to identifiers and discovery and description, and then basic messaging, like how do you move data from one point to another. And every time it gets to a protocol, it then gets into these questions of serialization. How do you put the bits on the wire in a way that the other party is going to be able to understand what they are and translate them into what they need? And so it's probably on this podcast not worth going too deep into what I often call the format wars or serialization wars. Certainly with verifiable credentials and the work at the for instance, W3C Verifiable Credentials Task Force, which is in its second generation, and also when we did the DID specification at W3C, we spent hours and hours talking about these different formats, JSON and CBOR and message pack. So we arrived at a conclusion that a bunch of work has gone on at Trust over IP into a specification called CSER, which stands for Composable Event Streaming Representation. But I think almost like 3 people in the world know that. Everyone calls it CSER. And It's actually really easy to describe. It was developed by Sam Smith, and it addressed this problem in a way that, as a protocol person, he just said, I just want to end the debate. Is text encoding better than binary encoding? Is it better to have something that supports streaming versus and pipelining versus message based? He just said, let's just end the discussion and have one serialization format that is optimized for cryptography and supports all these formats. You don't have to choose. You can just agree to serialize in Caesar. And again, I will just say this is a pretty deep topic. So in the blog post, we recommend, we did it at Internet Identity Workshop. I think it was last year. We did what we call we do presentations that are called Four Muggles, and they're just 7 parts, 7 minutes for each of 7 major points about whatever the topic is explained. 4 Muggles, and we did one called Caesar, and because it is a topic for developers, we call it Caesar for first-year wizards. And so we have a link to that in here. Anyone who's interested more about Caesar. But in the end, what it does, Mathieu, is it just means it doesn't matter what you want to ship over the wire. You can do it efficiently in a common language. I like the way you put it, that any trust over IP endpoint or intermediary is going to be able to understand and move around.
Kind of like having a guide to build a Lego castle. Like everyone has the same guide, they build it. So if I'm going to build it a certain way and you're going to build it the same way, and we're able to kind of share it with each other in a way that in our context here is about not structuring a Lego castle, but just messages in the same way, which just makes sure it's optimized for strong cryptography. I
like that analogy. Yeah. Exactly.
So we've touched upon the 6 pillars. So we have ways for 2 endpoints to kind of identify each other, and we've described it being broader than just a decentralized identifier, but a category called a verifiable identifier, which is more inclusive for other types of identifiers. We have our authenticity and confidentiality kind of method through ESSR, where we not only encrypt, but we sign things. We've talked about direct connections through inner and outer channels, which leverage both the verifiable identifiers and the ESSR. And then the same thing kind of in that 4th pillar via intermediaries, which give us stronger correlation privacy. We've talked about being able to do different relationship contexts through these same channels as the 5th. We've talked about structuring messages, just being able to talk to each other better in a standardized way through the 6th, text and binary encoding pillar. And we now move to the 7th one, which I would probably agree with you, Drummond, is going to be the most important one to just drive requirements and utility of the trust binding protocol. And this one has to do with trust task protocol framework, which I guess my first question is, like, we've kind of described what a trust task is, but are we thinking about one protocol for trust tasks with which we would then have multiple kind of more specific protocols for different types of trust tasks? What does this last pillar have to do with?
This is really the icing on the cake. And we call it a trust task protocol framework because, again, down at the level of layer 2, we're saying we just need to lay the framework, the foundation for any number of trust tasks. And if you think about protocol layering, we talked at the start of this about how in the TCP/IP stack, the internet stack, we've got TCP and UDP, for instance, layered right over IP. But you're still down pretty low down. But when you start moving up and you've got, you want to do email, well, that uses SMTP, which in turn uses, actually SMTP. I'm not enough of an expert to say, is that using, I think it's using UDP for packet exchange. But I'm not sure. And some architects are probably going to laugh and go, but HTTP is using, actually, I've learned in this very task force, HTTP, of course, was based on TCP, but because it's connection oriented and there are certain limits to that, which folks like my co-leads Sam Smith and Wenjing Chu would explain. They're now the newer faster forms and more efficient forms of HTTP are finally moving to UDP as their transport because of its scalability benefits. So, but in any case, these higher level protocols that are closer to applications or VoIP for moving around voice data, those are good examples of what you do at the higher layers in the TCP/IP stack. With the trust over IP stack, we're speculating. We don't know, of course, until they all exist. But we included in this blog post at least a dozen different common trust tasks that we believe will. And to answer your question, Mathieu, yes, they're protocols, but they're not necessarily heavyweight protocols. They don't have to do anything that is handled at layer 2 with what we talked about. All these other, the developers of those protocols can concentrate on just what do I need to do. For example, I want to send you. I'm a credit union, and I want to send you a wire transfer authorization form. I want to send it over a confidential channel. I want to make sure that you're the only one who can read it, who can fill it out, and then I need your digital signature on it in order to authorize that wire transfer. Right. So the application of a digital signature to a digital object or document like that, and the filling out of a form, those are not tasks. We don't want to have to design a protocol for doing that at layer 2. But we want to be able to say, hey, signing a digital document, sending it to the other party, having them sign it and return it and be able to verify the original sender. Yes, that was a document I sent and it's now been signed, and I can verify it was signed by the VID that I sent it to. I'm good to go, right? And there's an audit trail on both ends. That's extremely valuable. I would argue sometimes. Remember the huge difference in commerce it made when we introduced fax machines, right? And one of the huge benefits, or sort of unrealized benefits, was that you could take all of what you did with wet signatures on documents, and you can now do them at light speed, right? I could send you a contract, you could sign it and fax it back to me, and that was as good as if you'd sent it in the mail or hand it to me in person. Well, now we're saying, hey, we can do that with all kinds of documents and communications. We can rely on them because we're sending them over. We're getting all the benefits of this whole infrastructure that we've been describing. So, and that's just one example. That's signing a digital document. What if you want to have a standard way to not just purchase something over the internet, like a digital ticket, but then get the ticket back straight into your wallet and get a receipt for that straight back into your wallet, where you can prove to someone else not only that you used the ticket, but maybe that receipt for the ticket is something you can use to get a discount at the venue, right? Just dozens and dozens of other examples of the kinds of things that we could do if we had this trust infrastructure. And again, the thing about a trust task protocol is if we have this framework for easily the developers of those protocols just having to say, all right, I've got all this other infrastructure. I just need to say, here's the messages that are sent and received using this protocol. These are the roles that the parties using that protocol need to play. This is in their specification. This is the business logic, that needs to be applied. And here's the auditing or regulatory requirements that apply. All of those things can be specified, and now that protocol is available to anyone that needs to use that trust task. So we're going to make doing trusted, relationships and transactions over the internet exponentially easier, and that's why we're so excited about if we get layer 2 in place, then trust tasks can, 1,000 flowers bloom.
Wonderful. So just to close up, now we've kind of moved beyond the consolidation phase. We have this summary that we've tried to do today, kind of in response to the mid-year blog post, just to hopefully shed more information for anyone that's interested on what's happening with the trust spanning protocol. So as we close here, what's coming up? I assume there's movement towards kind of working drafts or just actual specifications of this thing, which implementers could then review and try to implement. So what's coming up? And maybe a side question here too, are there regulatory movements, and maybe just looking at one in particular with the EU Digital Markets Act, that kind of are perhaps creating a good moment for the trust planning protocol to solve some problems that are being pushed top down. So maybe painting a picture on the exciting future and what's coming up with around the trust planning protocol.
Absolutely. And in terms of logistics, that's exactly where we are. We ended the blog post by explaining we are now into the working draft stage. We are, we as a task force of Trust RIP, it's actually a task force of the Technical Stack Working Group, which I co-chair with Daryl O'Donnell from Continuum Loop, and most recently Kevin Griffin from Glyph has joined us as a third co-chair. We meet weekly. There are 2 meetings every week, one for North America, Europe, and one for APAC region, all on the Trust RIP calendar, which we also link to in this blog post, so it's easy to find. And we welcome anyone interested in this work, of course, to join us at Trust RIP, join this working group and task force. Our goal is to have a first working draft that really will be aimed at direct connections. We're going to make a sort of 2-phase in the drafting process to add the routing layer. But we want to IAW Internet Identity Workshop. I think only 3 weeks away at this point. It starts October 10th in Mountain View, California. We want to be looking at a working draft there and discussing everything we talked about here, but getting further down into the details. And I want to make it very clear, we want to complete those working drafts as soon as we can. We're really excited, we think, again, about this design, but we also want to have implementations. And I know I can't say anything right now because they haven't been publicly announced, but there are folks that are very excited about implementing it. And one of the reasons, as you said, or hinted at there, Mathieu, is with the growth of digital wallets and digital credentials, and I declined to mention, but the most prevalent trust task that everyone is focused on at the outset is issuance and presentation of digital credentials. Of course, those are trust tasks. Today, there's specialized protocols that have been developed to do that. And, OpenID for VC is best example. The European Union with their EIDAS 2 initiative has specified that's one protocol that EU digital wallets will need to support. The other one is the ISO MDL credential format and the offline presentation protocol that they have developed. These are, fantastic. I encourage folks. That's what a lot of folks are implementing because they exist today, and they're getting more mature, and they're getting a lot of testing. I'll point out Hyperledger Aries, they are using their credential exchange protocols are based on DIDCOM. They call them DIDCOM protocols, and that's the DIDCOM version of Trust Tasks. And they work fine too. So they're already, this sort of Trust Task architecture is being used for credential exchange. And what we are hoping is that as fast as we can move forward with Trust Spanning Protocol and then the trust tasks that are needed by the market, and those start to mature, that they will be able to then help us standardize on those on an even more broad basis. And in particular, when it comes to digital wallets and credentials, I'll put in a quick plug for the Open Wallet Foundation. Jen, that I work for, is one of the founding premier members, Open Wallet, and we very strongly believe in the need for open standard digital wallets, digital wallet ecosystems, and the broader and more powerful the protocols that digital wallets support, then the more that those wallets will be able to do for us, and that's why we do the work we do at W3C and here at Trust Over IP, and so. I really think that if we want to see this broad adoption of digital wallets and multi-purpose wallets that really make it easier for everyone, both consumers and businesses and governments, to have trusted digital infrastructure that's as convenient as many of the other things like credit cards and payment networks we have today, that protocols that have all these features built in are going to be one of the major things we want to leverage. And I'm super happy. I'm actually doing this podcast from the Linux Foundation Open Source Summit here in Bilbao, Spain, and we just had it announced. Google just made their contribution of libraries for MDL support. Actually, I'm learning they're even broader than that. Microsoft was just announced that they joined today, and we had several other projects. The first Hyperledger Aries project from Lissy and Asatis is going to be coming in. So I think it's a really exciting time for all this infrastructure that we need to come together. And if anyone is interested in really getting a full shot of this, by all means, come to Internet Identity Workshop. This will be number 37 in a couple of weeks. And that's where I'll next be seeing you in person, Matthew.
Thanks for tuning in today. Hope you enjoyed the conversation as much as I did. To stay up to speed with future episodes, or to catch up on ones you may have missed, make sure to check out the SSI Orbit podcast on your favorite podcast platform, and make sure you subscribe. If you have any questions, comments, or wish to see someone in particular on a future episode, you can find me by searching Mathieu Glaude on LinkedIn or Twitter. Feel free to reach out to me directly and I'll get back to you. See you all next time.